time is May 1982. The place, San Francisco Bay, California. As the SS Jeremiah O'Brien sails under the Golden Gate Bridge, several hundred people line her deck, admiring the spectacular view. But for most of them, this is no ordinary cruise. And indeed, this is no ordinary ship. For in 1978, the American government declared the Jeremiah O'Brien a national monument. A monument built not of stone, but of steel. It's true she doesn't seem very spectacular. Looking at her, you might hazard a guess, World War II, and you'd be right. A cargo ship? Well, right again. But underneath that ordinary exterior lies a story that isn't ordinary at all. For the SS Jeremiah O'Brien is the last of the Liberty ships. Built in enormous numbers in response to a wartime emergency, they represented a breakthrough in shipbuilding techniques. But at the same time, because of being built in haste, their rapid construction contained some flaws. The story of these flaws and what caused them was to become a landmark in the study of failure of materials under stress. So what were the Liberty ships? Why were they built? The story begins before America had even entered the war.
The blunt truth of this seems to be this, and I reveal this with the full knowledge of the British government. The present rate of Nazi sinkings of merchant ships is more than 3 times as high as the capacity of British shipyards to replace them.
In desperation, Britain turned to the United States for help. America was already supplying planes, tanks, and guns under the Lend-Lease Act, but ships were a problem. The need was for basic cargo ships, lots of them, and traditional shipbuilding methods were simply too slow. A new approach was needed, and it came from a man who'd never built a ship before in his life. Henry Kaiser was a construction engineer who had already built some of the largest dams in America, the Hoover, the Grand Coulee. Everything about him was big. Nothing was ever impossible. And when he turned his attention to shipbuilding, the results were quite astounding. What he introduced was nothing less than a revolution in shipbuilding techniques, a change almost overnight from a riveted to a welded construction. What this offered was speed and a new workforce. Relatively unskilled workers could build these welded ships remarkably quickly. Henry Kaiser might not have known much about shipbuilding. Indeed, he often referred to the front and back of a ship. But his great experiment in all-welded ship construction was an immediate success. The first Liberty ships, based in fact on a British design, were turned out in the short time of 245 days. Most of the ships were named after famous citizens. The first one, appropriately, after Patrick Henry, the 18th century patriot who earned his immortality with the phrase, "Give me liberty or give me death."
This is a memorable day in the history of American shipbuilding, a memorable day in the emergency defense of the nation. Today, from dawn to dark, 14 ships are being launched on the Atlantic, on the Pacific, and on the Gulf. And among them is the first Liberty ship, the Patrick Henry.
The traditional bottle of champagne was smashed on the 27th of September, 1941. As the shipyards got into the swing of things, there was an almost constant stream of ladies, fancy hats, and bottles of champagne. 245 days soon became 100, then less. It seemed that nothing was impossible. Finally, with the advantage of no blackout restrictions, a Kaiser yard built the Robert E. Peary in 4 days, 15.5 hours. Although partly done for propaganda, it was still an amazing achievement and an unbeatable record. Liberty ships were soon to be found in almost every convoy. They formed a significant part of the bridge of ships across the Atlantic. They were even to be found in the freezing Russian convoys, such as PQ-17 to Murmansk. But less than 12 months after the launch of the Patrick Henry, disaster was to strike, and from a source that no one could have predicted.
Report of structural failure of inspected vessel, United States Coast Guard. Name, Valery Chekalov. Course, Sovetskaya Gavan, Siberia to Akutan, Alaska. At noon on 11 December 1943, a loud report was heard, and 3 cracks were found. One on the port. The vessel was taken in tow by the tug Joseph Stalin, but at 22:06 hours on 13 December, she broke completely in 2. Classification of failure, broken 2. JLM Curry. Date of failure, 7 March 1943. Ship's location, Greenland Sea. The vessel came down on a very high sea and split in 4 places. The upper classification of failure, cracked deck. Name, John P. Gaines. Date of failure, at about 02:41 hours on 24 November 1943, an exceptional sea struck the port bow and boarded near the forward gun. The fracture immediately propagated. Classification of failure, broken 2. The bow is believed to have sunk.
Now, these cracks, sometimes so severe that the ship broke in 2, were obviously a serious blow to the war effort. But most worrying of all was the complete lack of any explanation as to why the failures were occurring. But one thing was clear. Many of the fractures seemed to be related. Many of them started from the same place amidships, in the upper deck, which suggested that longitudinal bending stresses were involved. A ship can be considered as a girder upon which a system of complex and variable forces is acting. Unequal distribution of cargo and ballast can cause the hull girder to hog, resulting in a maximum tensile stress in the deck, or to sag, causing a peak stress in the bottom. Wave bending moments can accentuate this effect. In practice, the laden Liberties often hogged, and the additional wave bending moment produced significant tensile stresses at deck level. Now, many of the fractures originated from specific structural features.
Apparent starting point. After starboard and forward port corners of number 3 hatch fractured in the upper deck. At apparent starting point, the fractures apparently began from the corners of number 3 and number 4 hatches in the upper deck.
This marking tape indicates one of the most common fracture paths. Starting at the corner of the number 3 hatch, the fracture would continue right across the deck. Openings in the side of the ship were another common starting point. Now, both these sites are places where we might expect stresses to occur. There's a weakening of the structure caused by a change in cross-section. But the weakening was much greater than was predicted. Consider a piece of metal upon which a force is acting. The force is transmitted through the material by what we can think of as lines of force. Now, keeping the force the same, we cut out a piece of the metal, producing a notch. The lines of force are redirected around the notch, as they can't, of course, cross the gap. And next to the notch, the increased density of lines represents a stress concentration. It's significant that if we remove the material on either side of the notch with the same force as before, the stress is now not as high. So the presence of the notch has produced a stress concentration out of all proportion to the reduction in cross-section. Most importantly, it's the sharpness of the notch that determines the increase in stress concentration. This can be visualized using the technique of photoelasticity. A light source, a polarizing filter, the specimen, and a second filter. The specimens are placed under an adjustable load. By rotating the front filter, fringes can be seen, which represent a contour map, lines of equal maximum shear stress. The load is the same on each specimen. As the notch gets sharper, the fringes change, indicating an increasing stress concentration. Orientation is another important factor. Which of these specimens would you expect to have the greatest stress concentration? The force is applied, and we see that where the slit is vertical, there's no stress concentration. It might as well be uncut. As the slit becomes more horizontal, the stress concentration increases. Can we use these ideas to help us discover what was happening to the Liberty ships? Well, there were obvious places where the stress concentrations were going to arise. The square corners of the hatches, for example. Now, square hatches themselves weren't new, but previously ships had been riveted. One advantage of riveting is that if one steel plate cracks, the crack is unlikely to spread to the next plate. The riveted join acts as a crack arrestor. The thing that was so different about the Liberty ships was that they were welded. If a crack were to start, it could run right through the hull with nothing to stop it. The ship was effectively a single piece of steel. But even if the square hatch corners were acting as stress raisers and the all-welded hulls had no natural crack arresters, fractures shouldn't have occurred so easily. Could there also be something wrong with the steel itself? Certainly it was behaving in a very brittle fashion, and not showing any of the toughness normally associated with a supposedly ductile material. One way of measuring the relative toughness of any steel is the Sharpie test. A standard steel bar is used with a 1 square centimeter cross-section. What's being measured is the amount of energy absorbed by this specimen when hit by the swinging hammer. The smaller the angle through which the pointer moves, the tougher the steel. But that toughness is greatly affected by temperature. A cocktail of methylated spirit and liquid nitrogen, stirred but not shaken, is used to cool the specimen. A larger angle, so the steel isn't as tough as it was. An extreme test involves cooling the specimen to the temperature of liquid nitrogen itself, minus 196 degrees centigrade. This is a very high quality steel. But at this temperature, it's totally brittle. No toughness at all. If we plot the Sharpie energy on the vertical axis against temperature, we get a characteristic graph. There's an upper shelf where the steel is tough, and this represents a ductile fracture. Looking at the fracture face, its rough nature is typical of a ductile fracture. Higher magnification shows this more clearly. On the lower shelf, the steel is no longer ductile and behaves instead in a brittle fashion. Looking at this fracture face, it has a characteristic flatness with small, bright facets. In between the two shelves, the fracture shows both brittle and ductile properties. The transition temperature defines the point at which it's exactly 50-50. There's the ductile region on the left, the brittle on the right. This steel is of high quality and remains ductile to extremely low temperatures. But the steels used in Liberty ships were of much poorer quality. As a result, the transition temperature was rather high, sometimes above room temperature. Many of the failures of Liberty ships occurred in cold, even Arctic conditions, where the steel would have been on the lower shelf and consequently extremely brittle. Examining the fracture surface from the hull of a Liberty ship, it shows all the signs of a typical brittle fracture, thus confirming our suspicions. The V, or chevron markings, are often found with brittle fracture in thin plates, and they give us an additional piece of information. They point back like arrows to the source of the fracture. Following them back, we come upon one of the final clues in the story. This fracture originated within a weld. Remember, fractures are much more likely to happen if there's something to initiate them. Have another look at the places where the cracks started. Yes, they started where there was a stress raiser, but coincident with the stress raiser, there was nearly always a weld. A weld effectively contains metal that has been cast and is therefore likely to have a lower toughness than the surrounding steel. But more importantly, a poorly made weld may already contain dangerous crack-like defects. It was these small cracks, depending on their orientation, that were the start of fractures that then continued right through the hull of the ship. So where exactly did the fault lie? Did Liberty ships fail because they were all welded? Or were the steel mills guilty of supplying brittle steel to the shipyards? Could the problems be put down to poor standards of fabrication, and in particular, poor welding, carried out by a semi-skilled workforce? Well, the blame can't be laid at any one particular doorstep. Rather, it was due to the coincidence of several factors. Design features like square hatches provided stress concentrations coincident with welds containing small cracks which could initiate a brittle fracture. The use of steels with a fairly low impact toughness, combined with operating conditions in low temperatures, meant that the steel was likely to be very brittle. The steel used did comply with every specification then imposed, although tests were required only at room temperature. And it was the same as that used in riveted ships without any problems. So what was to be done? There was no easy way to improve the quality of the welding quickly, and higher grade steels just weren't available. But something that could be improved was the design. In ships that were already operating, the hatch corners were given a somewhat makeshift reinforcement to reduce the stress concentration. Subsequently, the design of all ships was to include rounded corners wherever appropriate. Also, crack arresters were built into many ships. Strips of high-toughness steel riveted to the hull over which a crack couldn't jump. These were introduced in a number of locations and proved very effective. So a lot was learned from the Liberty ships, even if all the lessons couldn't be applied immediately. Of the 2,700 Liberty ships built, around 400 suffered fractures of some sort, of which about 90 were serious. In 20 ships, the fracture was effectively total, although less than a dozen ships actually broke in half. Even so, $50 million was the estimated total cost to the US government, an enormous sum of money at the time. In the longer term, much research was devoted to producing tougher ship steels that weren't substantially more expensive. Research that was also to contribute greatly to the present knowledge of the mechanics of cracked bodies, fracture mechanics. But the Liberty ships were much more than just a classic textbook example of a brittle fracture. It's important to remember that Kaiser's achievement advanced shipbuilding techniques enormously in a very short time. Today, for example, virtually all ships are welded. Even more important, perhaps, is their contribution to the outcome of the war. No less a man than President Roosevelt himself credited the Liberties with the saving of Europe. Carrying vital supplies, men and munitions to where they were needed, the Liberty ship became affectionately known as the workhorse of the seas. Jeremiah O'Brien herself made 11 round trips to the Normandy beachheads in support of the D-Day invasion. Now, fittingly, she has been declared a national monument. She and her sisters more than fulfilled the hope that President Roosevelt spoke of at the launching of the very first Liberty ship.
The Patrick Henry, as one of the Liberty ships launched today, renews that great patriot's stirring demand: give me liberty or give me death. There shall be no death for America, for democracy, for freedom. There must be liberty, worldwide and eternal. That is our prayer, our pledge to all mankind.
Thanks, Mr. Roosevelt, it's swell of you. See the British Empire smiling through stormy days have gone. And Franklin, by the way, please convey our congratulations to the folks in USA. We're saying thanks, Mr. Roosevelt, we're proud of you. All the way you're helping us.